Hello everyone. In today's lecture, we'll be learning about sympy. Sympy is a package in Python which is useful for symbolic operation in Python. Now, what it means for symbolic operation in Python. So far, we have learned about numpy, where if we are given a matrix in terms of suppose a variable x and y, and we can evaluate then the numerical value of that matrix by substituting the expression x with some numeric value. However, if we have some predefined matrix structure, we can use numpy to evaluate the matrix for different values of the variables of that matrix. However, in some cases, we do not even know the structure, or even if we know, suppose, the shape of a matrix, we do not know how would the different elements of that matrix would look like. So how can we automate that? Sympy does exactly that job. So suppose you have a matrix element, and that element of a matrix is changing for different dynamical systems. So suppose we have a mass matrix of a dynamic equation of motion of a manipulator or a robot, and different elements of that mass matrix changes for different manipulators depending on its shape or depending on its physical structure, how many degrees of freedom it has, all these different variables. So although all the manipulators has the same kind of equation of motion structure, however, different matrix in that equation of motion has different shape and structure. Sympy is one of the tool which we can use to basically compute the different matrices, suppose for the equation of motion of a dynamic model for different manipulators in a symbolic form, because for, as I said, for different manipulators that matrix structure would be different, and then we can convert that matrix which was expressed in symbolic form or derived in symbolic form at first, and then once we have that matrix in symbolic form, we can substitute those symbols with some numeric values. Now, when do we want to do that? As I said, that if the degree of freedom of a manipulator changes, if the structure, kinematic structure of a manipulator changes, the mass matrix of a manipulator will be changing for different manipulators. In those cases, we can take help from sympy package to derive the mass matrix for that particular manipulator, and then we can evaluate that mass matrix for different numeric values. Now, in order to use sympy, we need to have some imports at first. So let's import a couple of packages. So I'll first import the sympy package, and then another function called init printing, which you need to define at the beginning. So if you want to use sympy init printing for printing different variables, so I'll first import sympy package, and then I will say sp dot init printing, and as you can see that I am using Jupyter notebook. I am basically using that notebook in Google Colab, as you can see here. Next, once we have those imports, next we will define a couple of symbols. So in sympy, we can define symbols by using the symbol function. Let's see how it works. So suppose we want to define the symbol x and we want to use variable x for that. Whenever we want to use that symbol. So we define symbol x, and whenever we want to use that symbol we need to call this x. Okay. Next, suppose we want to define multiple symbols at a time, and we can do that too. So we can define symbols y and z as sp dot symbols method, and we can then define the symbols y and z. Okay. Next, once we have those symbols defined, we can define an equation. Suppose that equation is in terms of x and y, and we want to store that equation in the variable f. Okay. So we say f is equal to, suppose, x squared minus 2 times x times y plus y squared, and then I want to see how that function looks like, suppose. So I just type f, and here we get the expression that we get, and you can clearly see that the function f, or the variable f, which is actually an equation in terms of symbols x and y, when we print that f, we get the expression of that right hand side of f as x squared minus 2xy plus y squared in symbolic form. We do not need to have any kind of numeric values there. However, if we would have used numpy, we could not have done this. We would get error that there is no numeric values. However, using sympy, that is possible. We can evaluate f in symbolic form, and then comes the interesting part. So once we have that f in symbolic form in terms of x and y symbols, we can substitute different symbols with some numeric value, and that's one way we can evaluate this expression of variable f. So let's substitute x with 1, suppose. Okay. In order to substitute x, we just call the variable f and then call the substitute method, which is subs in sympy package, and then it takes 2 arguments, the symbol we want to make the substitute. So we want to substitute the symbol x, and with which numeric value you want to substitute x. So in that position we will give the numeric value, which is 1.0. Okay. Now if I hit enter, we get that y squared minus 2y plus 1, because if you look at this equation and if you look at this equation, wherever we had x, now that x is substituted with 1. However, we did not substitute y, so y is still there as a symbol in f. We can substitute y2. For that, we just need to follow the same method what we just did before. We want to substitute, suppose, y with 2, and we get this expression. Since in this case we have not substituted x, so we get the expression in terms of symbol x. However, in some cases we need to substitute both x and y with some numeric values. In that case, we would still call the subs method. However, in this case we need to provide a dictionary, and the key of that dictionaries will be the variables or the symbols that we want to make substitution, and the values of that dictionary would be with which we want to substitute. So if we want to substitute x with 1 and the symbol y with 2, then we need to make the substitutions like this. And now if I type s, we see that we get 1. And if we substitute this thing in suppose g and type g, then we get g is equal to 1. Okay. However, although we have made substitutions for the variables for the symbols of f, however, if we just type f and print f, we get the actual f expression with symbols x and y. So the variable f is still intact even after substitutions. However, if you substitute different symbols of f and store it in some other variable, then in our case we have stored the substituted expression of f in g, and when we print g we get the desired numeric value as we have seen here. So if we substitute x and y with 1 and 2 respectively in f, we get, and store it in g, we get g is equal to 1, which is correct answer. Okay, let's next talk about working with polynomials, because when we work with equation of motions of a dynamic system, many times we encounter polynomial equations of different variables, which will be squared to the power 4 of that variable. So it's good to know how to deal with polynomial equations in sympy. So let's define another variable p, which is a symbol and then let's take a function or variable f2, which is equal to p to the power 4 minus suppose 16, and then if we type f2, we see that f2 is p to the power 4 minus 16 in symbolic form. So far so good. Now suppose we want to simplify this f2 by factorizing it. So if we say factor, then this method will factorize the above expression, and we get p to the power 4 minus 16 is equal to p minus 2 times p plus 2 times p squared plus 4. Okay, sometimes, so this, let me comment this as okay. Next, in some cases, although we need to expand a polynomial, so let's first define another polynomial, and for that I'll first define one more symbol, which is r, and then I define another variable f3, which is storing a polynomial in terms of p and r suppose, So suppose that polynomial is p plus r whole to the power 4 times p minus 1 whole cube times suppose r plus 1. So this is my f3. So if you want to see how f3 looks like, so this is what f3 is. Now once we have f3, we suppose want the expanded form of f3. So what we do is we type f3 dot expand method, and we see that the expanded form of this expression is this one. Sometimes this is helpful. So I'll comment this as expanding a polynomial. Now suppose we are given another variable f4 and that variable is defined as p squared times cos. So in sympy package, if we have to use cos method, we need to call it as sp.cos, and suppose the expression is p squared cos p cube. Okay, and then if we have to see how that expression f4 looks like, it is like this. Now suppose we want to integrate this expression with respect to p. So if we have to do that, we would write I is equal to, which will store the integrated result, sp dot integrate f4 comma p. So what this is saying that, okay, use the integrate method in sympy package and integrate the expression f4, and the integration variable is p. So integrate over variable p. And if we do that, then after that if we type I, we get the integration of this expression with respect to p. Cool. Next suppose, so let me write it, comment it as integration. Okay. Next we'll look at how to differentiate a function in terms of p. So differentiate a polynomial slash okay. In that case, we see that all we have is already there. We have the function f4, and then we need to call the method diff. So diff is the method that we'll be calling here. So f4 the dot, we can do it this way or we can have this. So d is equal to, suppose we can call the diff method in sympy package and pass in the variable f4 and the symbol with respect to which we want to differentiate f4. So in our case it would be p, and then we see the result in D as this, and we can see that if we differentiate this expression with respect to p, we get this one, which is correct. In some cases, we also can define a differential equation and solve a differential equation, which is something we'll be looking next. Solving differential equations. So for that, we first define a function in sympy, which is h, and this function will be a function of symbol h. Okay, then we call another variable h2, which is suppose sp dot derivative. So that in h2 we are defining the equation or differential equation that we want to solve, to be more specific, and the differential equation is dx hx t of h with respect to x, so it is dh dx, which we write in this way. So derivative of hx with respect to x, that gives us dh dx, and then we are saying dh dx minus x squared times cos, suppose sp dot cos method x. So this is my equation of differential equation that I want to solve. Let's see how that equation looks like. So the equation is dh dx minus x squared cos x, and what we want out of this by solving a differential equation, we want to get the expression for hx, right? So all we have to do now, we can define another variable sol to hold the solution for this. Then we call the desolve method in sympy package, and what do we pass in? We pass in h2, which is the differential equation, and then we are saying that we want to solve this differential equation for hx. Okay, because as I said, we want to solve for this one hx, and that's what we are saying here, that solve for hx from the differential equation h2. Okay, and next we solve, print the solve, and we get that hx is equal to c1, which is an integration constant here in symbolic form, plus x squared sine x plus 2x cos x minus 2 of sine x, everything in symbolic form. And once we have that expression in symbolic form, substituting any numeric value for x or c1 would be easy. So no matter whatever x and c1 you take, we can always find the solution of this differential equation in numeric form. So that's the beauty of using sympy package. In some cases, we can also derive, we can also define, what do we say? We can define a expression which are in fraction, and then we can also evaluate its limits. So let's just have a quick look on how to work with that. So working with limits, suppose, so we define expression sp dot so we define the symbol L first, and then we say that L is equal to x squared minus x minus 2 divided by x squared minus 2x minus 3, suppose. So this is how L looks like, and we want to evaluate this expression when x tends to 1, suppose. How do you do that? So for that we say z is equal to sp dot limit, and we want L, and we say evaluate L when x tends to -1. Okay, and then we say what is my z, where, and z stores the limit, and we get the numerical value as 3/4. Now suppose we want to solve a system of equation, and before that we want to define a system of linear equations, suppose, and then we want to solve those system of linear equations. Okay, so let me define another symbol first. Let me define another symbol q, and symbol, after we define symbol q, we can define equation 1, suppose, as eq1 by calling the eq method or in sympy, which is basically to create equations, which is 2 times p plus 3 times q plus 5 times r, and the right hand side of that equation is suppose 8. So this equation 1 is saying that equation 1 is 2p plus 3q plus 5r is equal to 8. Okay, let's now define another equation, suppose equation 2, and we define equation 2 likewise equation 1. So it's, suppose, however the equation is different, so the equation is p minus q minus r is equal to 0, suppose. Okay, and then we define equation 3 as p plus r is equal to, suppose, 10. Okay, so we can define equation 1, equation 2, equation 3 in terms of p, q and r symbols. Now suppose we want that these symbols to be, once we have these equations in symbolic form, we can solve these equations for the variables, for the symbols p, q and r. And to solve that, we just need to call the solve method in sympy package, and solve method takes 2 arguments. The first one is a list of equations, in our case, which is equation 1, equation 2 and equation 3, and the second argument is which are the variables we want to solve these equations for. So we want to solve for variable p, variable q and variable r, and then we get p is equal to -4, q is equal to -18, r is equal to 14. So what we just did is we defined 3 equations as a system of equation in terms of p, q and r symbols, and then we just solve those 3 equations for the symbols p, q and r, and we got numeric values for p, q and r. Okay, now let's talk about how to work with matrices in sympy package. In order to define a matrix in sympy, we call the matrix method, and if it is a 2D matrix, then we need to define list within a list, and we say 1 comma x comma 5. That is the first row of the matrix. The second row of the matrix is suppose 0 comma 4 comma 6, all numeric values, and the third row is suppose combination of numeric and symbolic values. So its elements are minus 1 comma 0 comma x, suppose. Okay, now if you want to see how A looks like, A is something like this, where it has some numeric values and some symbolic values. Of course, we can substitute these symbolic values with some numeric values, as we'll see later, and that's one of the reason we are doing this tutorial, how to work with matrices with sympy package, which in case some matrix elements could be numeric values, some matrix elements could be symbolic values, and how can we evaluate those matrices number of time with some numeric values. And then suppose we want to substitute x with the value of 55, and then we get, sorry, I need to call a dot subs method. We get that in the places of x we now have 55, and if we just want to print A again, we see that the matrix A is intact and we just had substituted only once and it did not affect the actual A. We can also, like numpy package, find the shape of this matrix. All we have to do is just call the shape method and we get the shape of A is 3 by 3. Okay. We also need to sometimes insert rows and columns, and we can do that too. So for that we say that we want to modify A with some new row. So I say that A is equal to A dot row insert. This is the method for inserting row, and it takes two arguments, at which location I want to insert the row and what are the different elements of that row. So I want to insert that element, row element, at suppose position 1, and then we say that sp dot matrix, and notice that I am defining row as a 2D matrix. However, it has only one row. So in my case it's -2, 8, 4. And if I print A now, we see that I have actually inserted this -2, -2, 8 and 4 here. We can also insert columns. In that case, I can modify A as A is equal to column insert method, which is call underscore insert, and it also takes at which position I want to insert the column. Again, suppose I want to insert the column at position 1, and then I need to define the column. And if I type A now, we see that 0616 is sitting here at position. So this becomes the column 1 and this is column 0, since Python uses 0 indexed system. Okay, So now that we know how to define how to insert rows and columns, we can also delete rows and columns. Next we will look at that. And how to do that? I just need to call A is equal to, or I do not want to modify A, instead I just want to see if I delete a row, how from A, how would that look like, just to view the deleted row version of A. So I am deleting the second row of A, and then if I print now, we get that A is equal to this one, because we have deleted let me run this once again from top, because I think I'm facing some discrepancy in the result, because I have just deleted one row. Okay, now it gives the right result. So I have just deleted row 2 from here, and I see that the row corresponding to the element 0, 1, 0, 4 is now omitted. Okay, so A is now modified to this one. Next, we'll see how we can delete a column. In that case, we'll say that A dot col underscore del and the index of the column that we want to delete. In this case, we want to delete column index 1, and we print A, and we get this. And we can see that we have deleted column index 1, so the column corresponding to element 066 is now deleted. Okay. Next, suppose we want to access different elements of this symbolic matrix, and we want to modify such elements. So accessing and modifying elements of a sympy matrix, that is something we'll be looking at next. So suppose we want to modify the 0, 2 element with 6, or let me first show you what that element is, so that, okay, we say that that element is x, which is sitting here. And now suppose we want to modify that element with some numeric value, suppose 6, and if we print A now, we get that x is modified and A is modified and x is substituted with a numeric value 6. Okay. Next, suppose we want to get some slices of rows and columns. Slice of a matrix. And suppose we want to get the column index, row index 1. So for that, the syntax is very similar to what we have seen for numpy, and we just need to type A in square bracket the row number and colon to get all the elements. We get the corresponding row. Sometimes we are also interested in getting all the elements of a particular column. So in this case, if we are interested in getting all the elements of column 2, we type this and we get 6, 8 and 0. Okay. Now we'll see a really interesting thing in sympy, and we'll look at the lambdify function. What this function does is you can define any matrix or any matrix, suppose, in symbolic form in sympy package. So suppose let me first define a matrix in sympy, and then we'll see that how that symbolic matrix can be converted to a numpy array, and then you can evaluate that numpy array for any number of times, and that is faster. And this is an alternative way to do to do away with the individual substitutions of the different elements of a matrix. Instead, we can use this lambdify function to convert the entire symbolic matrix into a numpy array, and then we can evaluate it as per our requirement. So let's see what I just wanted to make. And let's first define a matrix in sympy. It's a 2D matrix, suppose, of size, okay, I'll define a 2 by 2 matrix. So we define the first row of that 2 by 2 matrix as x and x cube. Okay, then I define the second row as x to the power 4, x to the power 5, and we can see how the matrix B looks like. Yes, we need to have a square bracket here. We get the B matrix defined like this, and we want to see the type of that matrix, because we will be in the next couple of steps we will be converting this B matrix into some other package. Okay, we see that it's a sympy matrix, matrices dense, mutable dense matrix. So this is the class. However, what we want this matrix to be converted to a numpy array, so that we can evaluate this as many times as we want in numpy package. So in that case, we can define this as bnp, a new matrix, and then we are saying sp dot lambdify. We are calling this lambdify method, and we are saying that convert this B matrix into a numpy array, and then that matrix will have only one variable x, which will be substituting. So all it's doing is it's converting this B matrix into a lambda function, to be more specific, and this lambda function is a function of x now, and we can pass in numpy values, or we are actually converting this matrix into a numpy matrix from sympy package to numpy package. And if we type the print, if we print the type of bnp now, we will see what it is. So we see that bnp is now a function of x, and whenever we evaluate bnp, we'll get a numpy array. So let's now evaluate bnp for x value 2. So we just need to substitute, pass in 2, and then if we hit enter, we get a numpy array, and we see that all these x's are now substituted with 2 and evaluated. So we get 2, 8, 16, and 32 as the bnp evaluated at x is equal to 2, and also we get a numpy array. So that is the cool part here. So this is all that I wanted to show you for sympy package using, and hopefully this is helpful, and you will find its utility when you derive the equation of motions for a manipulator, and when you realize that for different manipulators, although the structure of the equation of motions are still the same, however different elements of that structure changes. So in that cases we need to use sympy. Thank you.